Okay, so hi everyone, my name is Elmer Bool. First of all, I'd like to thank you for accepting my invitation to this session called neurUL 101. To maximize the benefits that you might derive from these sessions, please mute your microphone when listening and unmute to ask questions or during discussions. Use your webcam so we know if we're getting you excited or sleepy. So any type of feedback is valuable. And feel free to leave comments and suggestions in the neurUL channel of Fibonacc after the session. So our objectives in this session are, first, to recognize problems common to all internet users today. Then we want to understand the proposed solutions to these problems. And we want to see how the neural powered future looks like. Then we want to understand theories and hypotheses in neuroscience, so the latest ones. And we want to use the same neuroscientific concepts to code in neurUL. So before we begin, I'd like us to start with a quote from Noam Chomsky, who is considered to be the father of modern linguistics. Wherein he says, universal grammar is a system of principles and structures that are the prerequisites for acquisition of language and to which every language necessarily conforms, which really succinctly defines what neurUL is. However, to deeply understand neurUL and not just define it, we need to see what it means for us as individual users. So let's start with the story of Steve. Steve is very active and always looking for ways to improve himself. He speaks English and Japanese. He's active on social media platforms such as Facebook, YouTube, and Twitter. He participates in trains for triathlons and uses a heart rate monitor to keep track of his performance, and his phone's GPS sends his location info to the servers of Facebook and Google. He uses various apps to manage his day-to-day activities, such as Google Keep and plain old Notepad, and he uses Asana for work. He has at least 15 connected devices at home, including an internet-connected fridge, a motion sensor, and a security alarm. He carries with him on a daily basis a tablet, a phone, a laptop, and an e-reader. His data is stored in 4 different cloud file servers, one for his personal files, one for a drive that he shares with his partner, another that he uses with his colleagues at work, and one he's been trying to get rid of, but cannot since it contains metadata that he's unable to export. Finally, his day job is as a business analyst. Life seems easy for Steve. However, he has in fact 4 main categories of interrelated challenges that aren't easily obvious to him. First, Steve is divided by hundreds of languages and vocabularies that he needs to be familiar with to navigate each domain in his life. In addition to human languages, he needs to learn professional languages, computer languages, application languages, device and platform languages. The list goes on, and it continues to grow each year. The multitude of languages result in barriers that make it difficult to explore any new domain and restricts Steve's opportunities, or at least the ones he's aware of. For example, Steve wants to learn how to code, but almost every year a new programming language or technology is introduced, each one always supposedly better than the previous one. He wants to study medicine, but the terms and concepts used seem so alien to him, and so he changes his mind and forgets about it. It's a very common problem. At work, as a business analyst, Steve works with all sorts of stakeholders: product owners, developers, testers, project managers, domain experts, and end users. And the interesting thing he noticed is that different groups of stakeholders use different languages to conduct their work. And these languages are actually causing more harm than good for their projects by creating more domain, technical, and human language barriers between the teams that use them. Now, for example, one of the users in one of his projects is a decision maker. And this user only wants to rename a label on a form, so this label here. To do this, the user reports the issue, Steve clarifies it, confirms the change with the domain experts, and documents the change request for the developers. But since the developers are currently working on something else, the change will have to wait until one of them becomes available. The change is then delivered 5 days after it was reported. Why? Simply because the decision maker can't speak or write in the language that the developers use to update the system. It's very difficult to find business decision makers who are able to code, and that's a reality. And it's unfortunate because really some simple changes take a lot of time because of this fact. At home, having no common language behind his tools, meaning his devices, apps, and appliances, he's further divided since they are not readily and inherently compatible. For example, Steve wants to turn off all notifications, but then the one from his microwave oven suddenly goes off. He plugs it off from the outlet to ensure it doesn't happen again, but then his doorbell goes off. Someone is at the door. He answers the door, then suddenly a Skype call rings on his laptop. Second, because of the divisions, Steve is perpetually delayed. For example, if he wants to know all important ideas he's recorded or that he realized while talking to someone, he'll have to use the search function, assuming that it's supported of each of the tools and apps containing his notifications, conversations, comments, posts, notes, calendars, files, folders, meeting notes, etc. Or on the other hand, let's say he wants to know the exact sequence of all events, then he'll need to go through the history, assuming again it's supported, of each of his tools and apps. His microwave oven, chat history, histories in Facebook, Asana, Google Keep, Dropbox, Windows, browser history, file system history. Then somehow consolidate all of these in his head to have a complete sequential view. And consequently, Steve is effectively disabled. Since he is unable to react with efficiency, he is rendered powerless against threats and opportunities when they arise. For example, let's say he wants to ensure that in case he gets into an accident while running, he wants his friends, relatives, and medical personnel to be notified urgently. But since he doesn't know how to code, and his apps are inherently separate and incompatible with one another, he's unable to configure and coordinate his tools so that vital information, such as his public post about his intention to run on Facebook, his GPS locations, selfies, and vital signs, and his fitness tracker, could be used to rescue him. Also, adopting new technologies becomes a pain, especially when different sets of his memories are committed to different platforms, apps, and devices. For example, Steve is beginning to like Android solutions, but he can't even try them since doing so would mean turning his back on all Apple products that he's been with in the past 15, 20 years. Finally, Steve is defenseless. Having his memories and control hosted by external parties mean that he is at their mercy in case an insider or the parties themselves abuse their powers. For example, when Facebook was involved in a scandal wherein data of millions of users were misused, he thought about getting his data removed from the social network. But after spending some time thinking about it, he realized that it's just too much trouble. He's already in too deep, and it's already too late. With so many tools to manage, he's unable to back up all of his data conveniently and easily to one's central location. If he manages to do so, he's able to do it for only a couple of his tools, his phone and his laptop. For example, he failed to make a backup of his Dropbox folder, thinking that its contents must be secure in the servers of the popular platform, only to find them all missing one morning at work. And still, he has to worry about his data on Facebook, his phone, his laptop, YouTube, his browser, etc. Finally, Steve wants to be able to customize his security. He wants to secure his information online as much as he wants, using as much resources he's willing to use for this purpose. Unfortunately, again, he's not in control. Like most of the tools he uses, his data is by default protected with only a username and a password. So to summarize, language barriers, which is where we started, ultimately make Steve divided, delayed, disabled, and defenseless. So it's really a complicated problem that surrounds Steve. So to go back where we started, what if there were no language barriers? What if we all used one language to simplify ourselves and our tools? One language to unify everything. So the problems that Steve has wouldn't exist if he had two things. First, a technology-enabled universal language or grammar that would underlie all knowledge work. A common language that will be used by all forms of intelligence, including artificial and natural, regardless of cultural or professional backgrounds. Second, an additional brain which will enable a flawless, portable, and centralized memory and control for each user. If Steve could speak a universal language, then he'll be able to minimize, if not completely eliminate, ambiguity and confusion. Using a meta-language, all recipients of his messages will be able to translate and clarify his meaning at their convenience. For example, instead of simply composing the sentence, "the house is green," Steve will be able to clarify and configure his meaning syntactically as well as the specific definition among many definitions for every word in his statement like this. At the other end, his recipients will be able to browse and explore each word, punctuation, or symbol as necessary, like a multidimensional network of information. So, for example, when someone says the house is green, there are so many possible interpretations for the word house and also green. But of course, it may depend on the context wherein this was mentioned. But if you were able to point to the exact definition that you're referring to for the word house, let's say house as a building structure and not house as a type of music, or green as a color and not a way of thinking, like being green-minded, then you can specifically define what exactly you mean in every type of communication that you're involved in. Then, secondly, if Steve had an additional brain to which he can connect all of his tools, then he'll be able to commit all of his memories and control, search and browse history, coordinate and upgrade, backup and secure in one central repository. So that is basically what neurUL will enable us to do. By using the neural network as a universal language, we'll be able to compose a new organ for each of us, for each of the users who would like to use it. So neurUL is short for Neural Universal Language. It is a free and open source project that is based on biological neural networks. And it is inspired by the idea that the neurons themselves actually represent a language and that the brain is itself a repository for this language. What would you do with an additional brain? What would you do if you had an additional brain? Can you have some answers to that question? Right, so there was a question, by the way, from Richard. Is it from Richard? Yep. Does that mean you want to create a super app like WeChat wherein you can do all the things? Luna, is that Mattias?
No, that's not me.
Ah, okay. Luna, who's Luna?
That's me.
Richard.
Message.
Richard, yes.
Yeah.
Richard. Yeah, so it's not really an app only. I mean, we can create apps surrounding neurUL. So, but then the back end, the coding language and the storage language, that will be neurUL. So, because all of the apps that we use at the moment, like Facebook, Google, Google search and web pages and all the apps that we have on our phone, they're all created using languages. So programming languages, database languages, and I mean, even the developers themselves and the people who develop these apps, they use everyday languages, like human languages, when they speak and collaborate with one another. And all of those languages are involved in developing those apps. So what we're saying is we're creating a new type of language which is technology enabled and is based on the neural network of our brains. And so by doing that, we attain the goal which was mentioned by Noam Chomsky, which is to create a language which should accommodate all possible languages. Yeah, so does that answer your question, Richard?
So you want to build a new computer language?
Yes, a computer language, but also a human that may also serve as a human language as well, and a way to represent information and also processes.
Okay, that sounds a little bit tricky to do.
Yeah.
Human and computer to understand the same language it's pretty hard. How can you do it?
Yeah. Naturally, uh, there are actually other similar efforts being done at the moment, which is the RDF, Resource Description Framework. So it's a technology being done by the inventor of the web himself. So he's leading that initiative. And his goal is to simplify the interface between different apps, different internet resources. So it's called the Resource Description Framework. And yeah, it's a really large topic. The main difference that we have with that solution is that we are mimicking the language behind our brains, the same capability, that the same functionality that enables us to communicate despite our different backgrounds as humans. Yeah.
Okay, so so what about NLP?
Yes, natural language processing.
Yeah.
Right. So for natural language processing, I understand that it uses machine learning, right, to process languages. And I think the parsing method, how it's being stored and so on. To be honest, I don't really have that much background in NLP.
Okay.
The only thing that I could say from neural's perspective is that we're able to represent the structure of statements of information using just the neural network. And that will be shown in the second session, actually. Unfortunately, not in this session, because this session is just for the basic structure and processes.
All right.
Okay. All right.
I'm pretty sure, Elmer, when we were trying to think of it, especially with the voice input, which I think, it took me a while to wrap my head around, and which you might be talking about too, is that as far as I see it, the NLP, or the natural language processing, so say you were using, like dialogue flow or something like that, that would sit on top of neurUL, so that it would process your natural language. You would have your NLP, and then that would feed into this to process that information that NLP has kind of broken down, because you still need to program out your NLP. Like, it's not super intelligent. Well, at least the stuff that I've seen. You still need to give it example phrases, so that it can infer based on 5 or 10 example phrases, associated phrases that would then have the same intent.
Right.
But that's still only can do that for a single language. Right.
Yes, and I think the common challenge is having the necessity for really large sets of data to be able to process it. So I think in neurUL it's much more simplified, because it's only just a matter of being able to parse the individual words, and then we will use neurUL to convert those words into actual responses.
Correct. Yeah. And there's still a layer of information, which I think you show maybe in the next session, that you showed me. There's still that layer of information and the library that needs to access. It's not like it just magically happens, right?
Right. And you can really see how this information is processed using the neurons themselves. There's nothing separate from the neurons in the processing. Yeah. Right. Okay. Right. So just a quick, so going back to the question, so what would you do if you had an additional brain? I'm actually about to show you guys a video of what's possible. So because we've just discussed the how neurUL can solve the problems which we discussed earlier. Now, in addition to solving these problems, what could be done if we had additional brains? So just to give you an example, I think what may happen is each user can then have his or her own set of brains, additional brains. So let's say I don't want to complicate my biological brain. So I have a brain for school, and I can have a brain for work, and I can have a brain for athletic activities. And then so my brain for my home basically memorizes all events at my home. So whenever my door opens, whenever someone moves, whenever there's some sound comes up at night, and so on. So that can be the brain for the home. And then I can have a brain at school that I would grow through time when I'm growing up. So all of the topics I've learned, all of the lessons would be recorded in that brain. And then when I start working, then all of the experiences that I accumulate through my career, I can then put in that school brain, and so on. But of course, that will turn into a new complexity if you have so many brains, right? So if you like, you can then merge those three brains into one, and so on. And there's also a possibility, although this will go through the verge of transhumanism, if you like. So that's the movement in Silicon Valley, wherein they're looking at how we can transcend our human limits. And so it may be possible, for example, if you have a brain which faithfully mimics your intelligence, then let's say after you expire, God forbid, then you can use that brain to allow your relatives or friends or whoever wants to learn from your experiences to consult you, using your experiences and using the things that you went through in life. So really, neural may be a solution to many of the limits that we have currently as biological creatures. Okay, and just to give you a nice example of what may be possible, let me just look for that session. So I'll just minimize this one. So this is a video. It's a Korean movie that I saw like a year ago when I was working on this project, and I think this may give you an idea of how it may work. Right. So all right. So that was a bit of an extreme example, but basically that is what neural may allow us to do, because if you have a central repository of all the events in your day-to-day life, let's say your Facebook activities, let's say you had a body cam on your person that you carry around with you, you have a sound recorder as well, and let's say all of the sensors at your home are integrated with this device in an Internet of Things, or rather an Internet of Brains, then you will have a sequence of these events automatically organized for you, and it's just a matter of playing it back and rewinding it when you need to. All right. So so are there any questions before we proceed to the neuroscience aspect, because that is where we'll start describing how neural replicates the natural version.
I'm good.
Yep. Okay. All right. So let me just maximize this one. Right. So we're just going to watch a couple of videos, so we can understand how the neural, how the biological neural version of the neural network works. Okay. So just let me know if you want me to pause the video so you can have a better look, or if you have any questions.
Welcome to 2-Minute Neuroscience, where I simplistically explain neuroscience topics in 2 minutes or less. In this installment, I will discuss the neuron. This is a brain. Estimates vary, but right now the best guess seems to be that our brains contain around 85 billion neurons. The neuron is a nerve cell, and it's the primary functional unit of the nervous system. This is a generic image of a neuron. Neurons actually come in all shapes and sizes, but this is the prototypical version of a neuron that you'll often see in a textbook. The structures extending from the left side of the neuron that look a little bit like tree branches are called dendrites. Dendrites are the area where neurons receive most of their information. There are receptors on dendrites that are designed to pick up signals from other neurons that come in the form of chemicals called neurotransmitters. Those signals picked up by dendrites cause electrical changes in a neuron that are interpreted in an area called the soma, or the cell body. The soma contains the nucleus, which contains the DNA, or genetic material of the cell. The soma takes all the information from the dendrites and puts it together in an area called the axon hillock. If the signal coming from the dendrites is strong enough, then a signal is sent to the next part of the neuron, which is called the axon. At this point, the signal is called an action potential. The action potential travels down the axon, which is covered with myelin, an insulatory material that helps to prevent the signal from degrading. The last step for the action potential is the axon terminals, also known as synaptic buttons. When the signal reaches the axon terminals, it can cause the release of neurotransmitter. These purple structures represent the dendrites of another neuron. When a neurotransmitter is released from axon terminals, it interacts with the receptors on the dendrites of the next neuron, and then the process repeats with the next neuron.
All right, so was that video clear? Do you guys have any questions about how a neuron works and the structure of the neuron? Okay, so let's proceed to the next slide.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge.
Okay, so that's just describing the process of the action potential. So it's just an impulse that travels from the dendrites to the soma, to the axon, and to the axon terminals. So it's just a one-way direction signal. It doesn't go back, right? So the signal comes from other neurons, right? And then goes into the dendrites, and then to the terminals and to the dendrites of other neurons. So it's a one-direction cycle. So just to see how it works from a high level, the next video shows us how multiple or neurons or neural ensembles work. Right. So that's the process called long-term potentiation, wherein multiple neurons that fire together consistently form stronger connections through time. So that's called the spike timing dependency plasticity. So if you have two neurons, let's say this neuron is dog and the other neuron is pain, for example, just as a very basic example of pain. Let's say the perception of a dog and then pain or a bad experience, then what happens is the connection becomes stronger and stronger to the point that when a dog is seen, automatically the experience of pain is felt. So that's how learning and training goes on in our heads naturally. Right? So you see stronger and stronger connections being made. And in cases wherein certain memories are not used, let's say the person no longer feels pain when seeing a dog, or when the person no longer feels something in relation to something else, then that connection is lost. And that's how we unlearn memories. Then again, a higher level view, you see signals passing from one neuron to the other and then forwarded to other neurons. Okay. Right, so a recent discovery, I think this is a, and I don't know the exact time, but this specific research was taken from last year, from an article last year. And what they're finding is, okay, so basically, let's start with the parts of the brain. So you have the occipital lobe here, where we have the visual cortex, and this is the parietal lobe. And this here is the front of the person's head, wherein we find the eyes. So what happens is when you see something, the signals from your eyes are sent to the visual cortex, right? And what they're finding is that the signals go from the eyes to the visual cortex, and then it's processed and sent forth toward the frontal lobe. Actually, to the parietal lobe and then to the frontal lobe. So that is the direction of information. But what they found was that when they asked their test subjects to close their eyes and to imagine the same thing that they just have seen, what would happen is the signals would start from the frontal lobe and then sent back to the visual cortex. So it's basically an inverse. And if you would think of an analogy for this, you could say that maybe there's a TV, there's a television in the brain of a person, and it's just a matter of the source, which determines what type of information is being processed. So if it is something that is seen, then the direction is from the sense organ to the visual cortex. But if it's imagination, then it's from here to here. All right. And another theory that is crucial in understanding neurul is this concept called the Hebbian theory, or the concept which says that cells that fire together wire together. So that's how we learn. That's how we get better at doing things. So let's say at the beginning you don't know how to swim, but then after years and years of swimming or years and years of playing football and so on, you get better and better, and you're able to configure your neural network so that you are efficiently configured to responding to events. Okay. Then the other concept that is crucial is the hypothesis of the grandmother cell. So basically, when you perceive something, let's say you have three concepts, right? Beautiful, sexy, and blonde. Now, when you see Jennifer Aniston, for example, these neurons, abstract neurons, are spiked, right? Now, the concept of the grandmother cell is that what happens is, using the Hebbian theory, we're able to interconnect different neurons together using another cell, so that when that cell is spiked, automatically those other neurons are spiked as well, using the action potential concept that we saw earlier. So this is it's a bit of a funny term that they've used for the grandmother cell, which is the Jennifer Aniston neuron. But basically, the idea is that we have specific neurons for specific ideas in our memories. So you may have a neuron for another actor, you may have a neuron for your favorite pet, for example. But then the idea is that those specific neurons simply wires all the neurons related to that specific memory. So this is a still hotly debated concept or hypothesis in neuroscience. They're still looking for ways to prove this, but what we're doing in neurul is using this idea and capitalizing on this idea and seeing if it can in fact support any data structure. And that's what we will see in if not in this slide, and a bit of it in the later slides, but we'll explain it further in the following session. Okay, so what we're looking at here is the flow, is a diagram which describes the flow of a reaction or of a sense input, which is then converted into an automatic response or reflex or reaction. So what happens is when we receive sensory input, let's say you touch or hot water touches your hands, right? So what happens is that signal travels to your brain, travels to your spinal cord, and then into your brain and into your cerebral cortex. And that signal is then converted into an action via a type of a neuron called the interneuron. So what happens is there's a neuron which converts those inputs. So a combination of inputs, let's say an input of the intensity of the heat or the location of the heat, and then they fire together to a point wherein that signal is translated and forwarded to another neuron using an interneuron, which sends back a signal to a muscle so that that muscle is moved away from that sensory input. So that's the important concept here to remember is the interneuron. Okay. Right, so let's see how we can use those neuroscientific concepts to encode in neurUL. So first, let us encode the basic concepts in this brain. So that will be Jennifer Aniston, Zach Galifianakis, and then Halle Berry, right? So we have 3 different neurons encoded here. Then we have other neurons for more abstract concepts called actor, funny, and sexy. Then since all 3 of these actors are actually actors, we connect an axon terminal from these neurons to the neuron actor. So just 1 terminal each. Then since only 2 of these actors are funny, we create a terminal from them to funny. And then since 2 of them are sexy, then we link these 2 actors to sexy. Now to encode actions or the response that we would like this neural network to perform, then we define cells for increase volume and call friend. So these are the responses that we would like it to perform. Then we create sensory event seen to indicate that this perception was received when through the eyes. So we create a neuron scene. And then we create a command for reaction because we want to be able to differentiate when we're only thinking of an action and we're actually about to do an action. So that's why we have a neuron here for react when. And we then create an interneuron which merges all of the input from the different neurons so that when react when, scene, actor, and funny are spiked, then this interneuron will fire to increase volume. So there is actually a mechanism used for this purpose called the synaptic strength. So there are cases wherein a neuron will only fire if all 4 inputs are received. Okay. So then going to the next one. Let's say we want to call a friend only when a sexy actor is seen, then we create an interneuron so that if actor, sexy, react when, and scene are spiked, then call friend is spiked as well, since we have an interneuron linking them together. So based on this very simple example, we can see that increased volume will happen if only Jennifer and Zach are seen. So if Jennifer and Zach are seen, then by following their action potentials, this will be spiked. But if Jennifer and Haley are seen, then call a friend will be spiked. And as you can see, Jennifer will be spiked in both cases because Jennifer is both an actor, is both funny and sexy. So this is able to simulate the same if conditions and switch conditions that we have in regular programming languages at the moment. Okay. So any questions regarding this? How we're able to convert perceptions into actions and create responses based on it? Okay. All right. So to summarize, we were able to recognize problems common to all internet users today. We also understood the proposed solutions to these problems and how a universal language can be used for and could be used to create an artificial brain, as well as to unify our different platforms and tools. And we also had a quick look at the potential for having a neural powered future. So what if our apps, what if our devices and our solutions use neural in the background? We also looked at neuroscientific theories and hypotheses and how we use these concepts to code in neurUL. All right. So in the next session, which is actually something that we're going to go through after this session, we are planning to see how neurUL is how neurUL uses actual programming concepts and language concepts, so that we're able to actually support different languages that we are using currently. All right, so all right, that's it. Thank you very much for
all that we desire.